In this video, we will start discussing antiderivatives, which are also called indefinite integrals. So, until now, we spent a lot of time computing derivatives of functions. And now we are going to look at this problem in the opposite direction. Given a derivative of some function, let's say this derivative is f of x, we want to know which function has this derivative f of x. And this function that we want to find is called antiderivative of f of x. Another name that we use for this antiderivative is indefinite integral of f of x. And when we want to write this antiderivative or this indefinite integral, the notation that we use is this integral sign f of x dx. Now, using this new terminology and this new notation, asking which function has this derivative f of x, it's the same as asking what is the antiderivative of f of x. And if you can find some function, let's say a of x, which has this derivative f of x, then you can say that antiderivative or indefinite integral of f of x is equal to this function a of x plus a constant c. Now, the reason you have to add plus c is because if your function a has this derivative f of x, then this function a plus a constant also has this derivative f of x, right? Because the derivative of a constant is 0. And you can also see this graphically because adding a constant to a function just shifts its graph by this constant. But of course, it doesn't affect the slope of the graph. And it's very important to remember to write this constant plus c because in many applications, we will be given some additional information which will tell us what this constant c is. Now, in calculus, there will be many applications of antiderivatives. But first, we'll spend a lot of time just learning how to compute them. And so to get some idea about this part of calculus, let's take a look at several examples of antiderivatives. Now, in this first example, we say that antiderivative of cosine is equal to sine. And of course, this is because at some point we already computed the derivative of sine, which we know is equal to cosine. So now we are just rewriting the same statement using this new notation. And in the same way, we can just go through the list of derivatives of basic functions that we already computed and rewrite those statements using this notation and this terminology of antiderivatives and indefinite integrals. But of course, pretty soon we are going to run out of those examples. So what we are going to do next is reverse engineer some of the rules for computing derivatives. For example, here, if you look at this function e to the x squared times 2x, you might notice that this 2x, it's actually a derivative of this x squared inside the exponential. So you might recognize that a chain rule was used here, and if you notice that, then you can see that the antiderivative will be equal to e to the x squared plus c. Now, this reverse engineering of the product rule will be called integration by substitution. And often it will be used in combination with other tricks for computing integrals or indefinite integrals. Now, in this next example, to compute this antiderivative of e to the x cosine of x, it will be a little bit more complicated. And to get to the answer written over there, we'll have to reverse engineer the product rule for computing derivatives. And in this context, this will be called integration by parts. And finally, in this last example, the function e to the minus x squared, it looks pretty simple. But it turns out that there is no way you can write its antiderivatives using the basic functions that we are familiar with in calculus, like trigonometric functions, exponential, logarithms, inverse functions, and so on. In this particular case, this function in some sense is lucky because it appears so frequently in applications that people actually gave its antiderivative some special names. For example, one of the names is the error function, up to some constant written here. But if you think of some random function, and if that function is complicated enough, most likely its antiderivative cannot be written using our basic functions in calculus. And unless that function is used frequently in applications and its antiderivative has some special name, the only way that you can compute its antiderivative is actually numerically on a computer. So if you want to learn how to compute antiderivatives numerically on a computer, this is something that we will discuss when we talk about definite integrals and the fundamental theorem of calculus.